All right, we're going to do our third video for 3.9. This is derivatives of general exponentials and logarithmic functions. So instead of doing e to the x or ln of x, we're going to look at a general base b. So we'll have b be greater than 0. B does not equal 1 because it makes it a stupid problem. 1 to the anything is just 1. And we'll let g of x be a differentiable function. If we have y equals log base b of x, then y prime or dy dx equals 1 over x times the natural log of b. And the chain rule also applies if we have log base b of g of x equals h of x, then h prime of x equals, we do 1 over the log, or 1 over what's inside the log, so 1 over g to the x, we have the natural log of b on bottom, and then we do g prime of x. Proof, I'm going to do it using the change of base formula. I think they do something a little different in the book, but we can rewrite log base b of x. There's a couple ways you can write it. You can rewrite it as any base you want. Common ones to use are log base 10, because that's what's on a calculator, pretty easy, and so is natural log. But whatever's here goes here, and whatever's here goes here. We're going to use this one because we just did the derivative of ln of x earlier. But I wanted to show the common change of base formulas. So if we do that, we've got this equals y. And I'm going to rewrite that by putting the ln of b on the bottom out front as 1 over ln of b. That's just a constant. It's like a constant k. So when you take the derivative, you don't need to take the derivative. We got y prime of x equals 1 over ln of b. That's what we had. The constant, the derivative of natural log of x is 1 over x. So we get y prime equals 1 over x times ln of b. That notation looks funny. I think I wanted to say y prime equals dy dx, and I got crazy. Chain rule proof is similar. If you want to do the proof of it, go ahead and work it out doing the same things we did here. You would get a g of x in here, and then you got to take the derivative of that. Then let's look at the other one, the general exponent. If y equals b to the x, then the derivative of y dy dx equals b to the x ln of b. And the same thing if we want to do the chain rule version, if h of x equals b to the g of x, then h prime of x equals b, the original one, b to the gx, times the derivative of the exponent, and then times that natural log of b. So proof y equals b to the x is the same as writing log base b of y equals x, and that equals ln of y, ln of b. When I clear fractions, I move the ln of b to the other side. By multiplying through, I get that. Now we have to use implicit differentiation. The derivative of ln of y is 1 over y times dy dx. The derivative on the right side is just natural log of b. We multiply both sides by y. We get dy dx equals y times natural log of b. But y equaled b to the x. Look at that. So we get b to the x ln of b. So those are the two formats. So if it's not a base E, there's going to be an L. If it's a different base, B, there's going to be an ln of B somewhere. On the exponents, when it's b to the x, it's just multiplied by ln of b. When you're doing the derivative of natural log of x, the ln of b is on bottom. Something to just memorize. Let's find h prime of x if h of x equals 2 to the 4x squared. So we've got, that's at base 2, so we're going to have an ln of 2 when we take the derivative. And then we got to take the derivative of the exponent. So d dx of 4x squared, that would be 8x. Notice I do not combine the two and 8x. They are separate. You cannot put them together. It is not 16x to the 4x squared. Don't do that. Don't combine them. Leave them separate. You probably wouldn't have combined the ln of 2, but I see a lot of students generally trying to combine the 2 and the 8 to make it 16. And that doesn't work here. Then let's take a look at a problem where you find the slope of the tangent line to y equals 4 times log base 3 of 2x cubed plus 2. And we'll find the slope at x equals 1. So we got to take the derivative. Remember, the slope is dy dx evaluated at the point. So here we've got 4 over the derivative of the inside, or 4 over the inside, so 1 over 2x cubed plus 2. Since it's a different base, we have a natural log of that base down below, natural log of 3 down below. Then we got to take the derivative of the inside. When we do that, this part right here is 6x squared. So we get that. I multiply the 4 times the 6x squared. I've got 24x squared on top. 2x cubed plus 2 times ln of 3 on bottom. You don't want to, it doesn't split up. Don't split this. Don't try to split this because it doesn't split. You can only split stuff when the plus is on the top, not on the bottom. We wanted to find the slope at x equals 1 though, so you can plug 1 in, and we've got 24 times 1 squared on top. That's just going to give us a 24. And then on bottom, we've got 2 times 1 cubed is 2 times 1 is 2, plus 2. We got 24 on top. We've got 4 times natural log of 3 on bottom. So we get 6 over the natural log of 3. If you need a decimal value, you can do that. But if you were to graph this like in Desmos, I would just use 6 over natural log of 3 and don't use a decimal. Okay? Here's one for you to try. Find the slope for the line tangent to y equals 4 to the x power at x equals 2. Pause the video and work it out. All right, I'll assume you did. Remember, the derivative of b to the x is just b to the x times natural log of b. So we have dy dx equals 4 to the x times natural log of 4. We evaluated at x equals 2. We got 4 squared natural log of 4. So the slope would be 16 times natural log of 4. Again, stuff doesn't combine. I mean, you could do this, ln of 4 to the 16th power, but why would you ever want to raise anything to this 16th power? So it's just 16 natural log of 4, whatever that value is, and calculate it. If you need a decimal, go with it. Next, we're doing logarithmic differentiation.